We are looking at independent and dependent events. Okay? And probability of things happening when it's dependent and independent. Learning goals. I am learning to describe and determine how the probability of one event occurring can affect the probability of another event occurring. And if we've already done things like this, we want to solve the probability problems involving multiple events. So when different events happen and they depend on each other, or if they're independent, we'll figure out how to solve it in both ways. So compound events, this is a definition that we need. Multiple events in a probability experiment may or may not affect each other, okay? So multiple events is a compound event. Independent events, situation in which the occurrence of a or non-occurrence, so if something happens or doesn't happen, of one event has no influence on the probability of the other event occurring. So one event has no bearing on the other. The occurrence or non-occurrence of one event influences the probability of the other event happening. So if something occurs or doesn't occur, it'll depend. It'll influence the probability of another event. And finally, conditional probability, probability of a second event occurring given the first event already occurred. So the sample place for the second event is reduced from the first event. This is very important. And you should write this down and kind of highlight it because that's a way that you can understand most of these questions. All previous examples have been independent events. Three-coin toss. So most of them. There's one scenario where it wasn't. Or rolling of two dice. If you roll a dice or you roll a second dice, it's an independent event, right? The first coin toss doesn't depend on the second coin toss. And I remember, if you remember the bag and the marble scenario, we always put the marble back. So it was independent. My first trial of taking out a marble was going to be different from any other, it was going to be the exact same, it would be independent, the result of my second sample of the bag of marbles. Okay, so let's learn by example. We're learning about independent events. Olivia has 4 highlighting pens in her pencil case. Yellow, 1 orange, and 1 blue. After she uses it, she immediately replaces it in the case to be used again. So she immediately replaces it. What is the probability? What is the probability that she will choose 2 yellow highlighters in a row? So the fact that she's putting it back means the probability doesn't change the second time she pulls it out. If she kept the highlighter outside the bag, I don't know why I tried to draw a highlighter there. If she removed it, it'd be a different story. Then the probability would change. But in this case, it's an independent event. Both times she takes out the highlighter. So what is the probability that she will choose 2 yellow highlighters in a row? So a yellow highlighter followed by a blue highlighter. So the first trial. Okay, so 2 yellow highlighters in a row. So she has 2 yellow, 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 oops, 1 orange, and 1 blue. And then each of these has the same probability: yellow, yellow, orange, blue, yellow, yellow, orange, blue, etc., etc. So in order to draw this, we're going to have another 4. So maybe I should draw it a different way. But the point is, n of s is going to equal to 16. Okay? So, and there are how many scenarios where she pulls out 2 yellow highlighters? Well, let's take a look at that. That's yellow, yellow. That's yellow, yellow. There's 2. That's yellow, yellow. And that's yellow, yellow. So the event n of yellow, yellow, we'll call it YY, is equal to 4. So the probability of 2 yellow highlighters is going to be, of 2 yellow highlighters, is going to be 4/16 or 1/4 to do it twice in a row. Okay, what's the probability of a yellow highlighter followed by a blue highlighter? Well, there's only 2 scenarios where that happened. Clear pen marking. Let's try doing it one more time. Okay, we got yellow, yellow, orange, blue. And then this one we got 1, 2, 3, 4. Yellow, yellow, orange, blue. Yellow, yellow, orange, blue. Yellow, yellow, orange, blue. Yellow, yellow, orange, blue. So yellow, yellow, orange, blue. Yellow, yellow, orange, blue. Yellow, yellow, orange, blue. Okay, so yellow highlighter followed by a blue. 1 case, followed by a blue. 2 cases. So that scenario will entail that I have 2 out of 16. Probability of yellow-blue equals that, because n of yellow-blue is equal to 2, n of s is still equal to 16. Okay, so that's by counting. Okay, but she immediately replaces it into the case to be used again. Let's clear the markings. Because she replaces the pen with the same color, each picking of the pen is independent. If she did not replace it, oh, so we did it already here. Okay, so 2 yellow highlighters in a row. We already did that, it's 25%. Yellow, blue would be 2/16. So I guess I should have moved along. So independent events. Here's a different way to do it. If I have 2 yellow highlighters in a row, first draw, what is the probability of picking 1 yellow? Second draw, what is the probability of picking 1 yellow? So the probability of picking a yellow is 2 out of 4. What about on the second draw? It's the same. Probability of picking up a yellow is 50%. So when they're independent, I can multiply these probabilities. The probability of the first event multiplied by the probability of the second event, which is 25%, which is the same answer we got when we counted out every single outcome. How about a yellow highlighter and a blue highlighter? So the first draw, what is the probability of picking up a yellow? And on the second draw, what is the probability of picking up 1 blue? So in this case, there's 2 out of 4 yellows to pick. And on the second draw, the probability of picking up a blue, I guess I have to do that. Probability of a blue is actually 1 out of 4, right? So probability of a blue is probability of a y, which is 50%, half, and probability of the blue is 1/4. So probability of picking up y blue is actually that. Y blue. So that's 1/8. That's y blue. And it ends up being 12.5%, which is pretty much the exact same answer we got when we counted it in the using a tree diagram. So here's the multiplicative principle, fundamental counting principle for independent events. It says the probability of two independent events, A and B, occurring is probability of A and B is equal to probability of A multiplied by the probability of B. Okay? So don't confuse independent events with same trial events. Okay. Different compound events. A game is played with a die and a spinner. Player A wins a point if the spinner lands on red and rolls an even number. Player B wins a point if the spinner lands on yellow or green and a composite number is rolled. What's a composite number? It means a non-prime number. Is it a fair game? And how do we know if it's a fair game? If the probability of the same thing happening is the same, then it's fair. A composite number is an integer greater than 1 that is not a prime number. Okay, both events are independent. We'll look at player A first. Okay, is the spinner going to have an effect on the dice? No. So let R represent that A spins red. Okay? And let E represent an event where A rolls even. Player A. So PR is 1/4. And P even, basically, it's 2, 4, and 6, right? There's 3 out of 6. Actually, let's do the right notation. E is that, right? So it's 3 out of 6. So here's now how we say and. I want you guys to know this notation. Before we were just saying and. Now you say and like that. Almost like an A, but not. It's an upside down U. Okay? The probability of red or E is, multiply it because they're independent, 3 over 6 times 1/4. And that's equal to 3 over 24. 6 times 4 is 24. And we simplify, we divide both by 3. We get 1 over 8. And the probability A gets a point is 12.5%, which is 1 over 8. Now we look at B. B wins a point if the spinner lands on yellow. Both events are independent. A represents the event B spins green or yellow. Okay, so when does B get a point? When it's green or yellow. Green or yellow, that's half the time. And C represents B rolls a composite number. Well, what's a composite number? Well, that's not right. That's actually half. PC equals 2 over 6. Well, what's a composite number? It's greater than 1. 1 is not a composite number. 2 is not a composite number. 3 is a prime number. 4 is a composite number. 5 is a prime number. And 6 is a composite number. It's composed, right? So 4 and 6 are composite numbers. Oh. That's 2 over 4. Yes? So that's why it's 2 over 6. So we got 2 over 4 multiplied by 2 over 6. We got 4 over 24. And we divide both sides by 4. We get 1 over 6. So the probability A gets a point, that's B gets a point, is 16.7. So is the game fair? It's not fair. B is more likely to get a point than A. The game is not fair. Okay, here's the same question using a tree diagram, right? So look at this. Player A wins in these scenarios, right? Red, and then I get a 2, a 4, and a 6. And B wins in 4 different scenarios, yeah? Yellow or green, and 4 and 6. So 4 different scenarios. And it just so happens that because they're independent, you can multiply both events both events. But you see that this is definitely B has more opportunity to win than A. All right, now let's talk about dependent events, which are a little bit different. 2 red checkers and 2 red marbles are placed into a bag. So we put these into a bag. And what is the probability that a red checker is randomly chosen followed by a second red checker. Now, no replacement occurs. So let's evaluate this, okay? The probability of picking a red is half. Got that there. Now, if no replacement occurs, on the first try, probability is 1 over 2. But on my second trial, like, this is what can possibly happen. See, here's the thing. There's two events that can happen. On my first trial, I could take a red, but I could also take a black, right? And so my scenario changes in both scenarios. On my second try, taking a red is 1/3, or it could be 2/3, right? So what do I do? Well, the probability of taking a red is 1/2 times 1/3. If I pick the black checker first, then I'm not going to pick two red ones anyway. So I'm not going to pick, this doesn't really matter because I'm not going to pick a red one, right? You can't multiply them together because, well, they're not independent events. It changes, right? So that's what I have to look at this, right? I have to look at this scenario. Okay, let's formalize it with an equation. Okay, let's take a look at that. There's a 50% probability that I'll end up right here and a 50% probability that I'll end up here. So if you didn't understand that perfectly, let's take a look at that. There's a 50% chance probability I'll end up right over here. Okay, so if I end up here, the only way I can take two reds is right here, right? So the only way I can take this third right here is if I ended up here in the first place, right? So that's why I multiply these events right there, 1/6. Okay, multiplicative principle for dependent events. To calculate the probability of two dependent events, A and B occurring, multiply the probability that A occurs by the conditional probability that B occurs, given that A occurred. Okay, so the probability that A and B happen, that means I pick a first and I pick a second, is the probability that the first event happened multiplied by the probability that B happens given A already happened, right? This here, let's go back. Let's clear this so we can see it again. This here is a probability that only exists if this happened. This here, if A is red, A is red first try. Then B, this is a 1/3 probability given that A already happened. Okay, and that's what this part of the equation does. It's saying that the probability of B happening given that A happened. So what we need to have happen before the second event times the second event assuming first event took place. So let's look at this telemarketing example. Telemarketing example. Data from 1,000 calls shows that the probability of a caller staying on the line for at least 1 minute was 16%. So we have a caller staying online 1 minute. or they can not stay 1 minute. And this is 16%, which means that this is 84%. The conditional probability that a call results in a sale, given the caller stays on the phone for a minute, is 25%. So here, sale, no sale. So if you keep a person on the phone for a minute, given the caller stays on the phone, the sale will occur at 25%. No sales were made if the receiver did not stay on the line for at least 1 minute. So this is also no sale, 100%. Okay, so what percentage, okay, P of M, that's for minute, and S, what's the probability of they stay on the phone and they make a sale? Well, that's the probability that they stay for a minute, multiplied by the probability that they stayed for a minute and made a sale. Sorry, the probability of a sale given that they stayed a minute. So what's that? That's 0.16 times 0.25, which is 0.04. So 4% of 1,000 calls resulted in sales. So draw a tree diagram to the checkered problem to make sure that, convince yourself that the formula makes sense. Okay, so the checkered problem was the following, right? What's the probability that I have red, red, black, black? So what can I do? I have red, red, oops, black, black. And I'll call it red 1, black, red 2, black 1, black 2. And if I took a red one, what do I have left to pick? R2, black 1, black 2. R2 results in red 1, black 1, black 2. If I take the black one, then I can do red 1, red 2, black 2. And then I have red 1, red 2, black 2. Now, which ones? What's the probability of picking a red? Double reds? We got this red. We have this red, which is essentially, n of RR is equal to 2, and n of S is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then P of RR is equal to 2 over 12, which is equal to 1 over 6. Is that what we got? Let's do the calculator. Oh, there's no calculator on this. Let's just check our previous results. What was our answer? It was 1 over 6. So it makes perfect sense. Okay? And that's all for this video.